Have you ever really thought about what happens when you transfer money? You know, how it zips between computers that could be thousands of miles apart and still works perfectly? Or how your cloud files just stay safe? Well, it all comes down to one big idea: making sure that in this giant, messy world of connected computers, one little failure can't bring the whole thing crashing down. Today, we're going to pull back the curtain on the super clever rules that keep our digital world running.
So here's the plan. We'll start with why our data is so spread out to begin with. Then, we'll get into the critical all-or-nothing promise these systems have to make. After that, we'll dive into the protocols that make it all happen, focusing on a classic called the two-phase commit. And finally, we'll connect it all back to why this stuff really matters to you. Okay, let's jump in.
All right, first things first, let's get a handle on the world we're living in. It's a world of distributed data. Right now, you might think your files, your bank account, your photos, that they all live in some single, neat little digital box. But they almost never do. In reality, they're part of what we call a distributed system, spread out across tons of different computers, sometimes all over the globe.
To make this real, just picture an engineering firm. They've got offices in Boston, Paris, and San Francisco. Now, they all need to work on the same projects, right? Access the same data. So instead of having one massive, slow database in one city, they use a distributed database. Each office has a piece of the puzzle, but to them, it all works together like magic. So why go through all this trouble? Well, the perks are huge. You get way better performance because you're splitting up the work. You can scale things up just by adding more cheap computers instead of one crazy expensive one. And here's the big one: fault tolerance. If that Paris office has a power outage, the whole company doesn't just grind to a halt.
And that, right there, is the million-dollar question. This whole setup is powerful, for sure, but it's also kind of fragile. What happens if the computer in Boston crashes right in the middle of updating a project budget that Paris needs? How do you stop the data from turning into a complete and utter mess?
This brings us to the most fundamental promise that any reliable database has to make. It's non-negotiable.
See, any operation, whether it's updating a budget or moving money, is called a transaction. And for it to be reliable, every single transaction has to follow 4 sacred rules, known as the ACD properties. That's atomicity, consistency, isolation, and durability. We're going to zoom in on that first one, atomicity.
Atomicity is the all-or-nothing principle. It's like the word says, atom, it can't be divided. A transaction either succeeds 100% across every single computer involved, or it fails completely and the system just rolls back and pretends it never even happened. There's absolutely no in-between.
Think about how critical this is for a bank transfer. You take money out of one account and you put it into another. If the system fails after the money's been taken out, but before it gets put in, that money just, poof, it vanishes into thin air. Atomicity is what prevents that nightmare scenario. The whole thing is one single, unbreakable step.
Which leads to the obvious, kind of scary question. How on earth do you guarantee this all-or-nothing rule when your computers are scattered across the planet, and any one of them could just die without warning? How do you get them all to agree on what happened?
The answer, it turns out, lies in a set of really clever, really strict rules of communication.
We call these distributed reliability protocols. You can think of them as a formal script, a procedure that every computer involved in a transaction has to follow to the letter. The whole point is to get everyone to agree on one single outcome. Either it's a go or it's a no-go, before anyone dares to make a permanent change.
Most of these protocols work with the coordinator and some participants. So you have one boss, the transaction coordinator, who runs the show. And then you have the workers, the transaction managers at each location, doing the actual work. The coordinator's only job is to make sure everybody is on the exact same page.
And the classic, the foundational example of these protocols, the one we're going to break down right now, is called the two-phase commit protocol, or, 2PC for short.
All right, let's get into the nitty-gritty. How does this thing actually work?
Well, like the name suggests, it all happens in 2 main phases. No surprise here. First, you've got the voting phase, and second, you've got the commit phase. Nice and simple.
So in phase 1, the coordinator doesn't tell anyone to do anything. It just asks a question. It sends out a prepare message to all the participants, which basically means, hey, get ready to make this happen. Can you promise me you're ready and able to do it? Each participant then does a self-check. Can I actually do my part of this deal? If the answer is yes, it writes down what it's going to do in a temporary, super safe place called a log, and then it votes yes. And this is the most important part.
A yes vote is a binding promise. It's a contract. It's saying no matter what happens next, even if I crash, I swear I can finish this job if you tell me to. If it can't make that promise, it votes no.
Then the coordinator collects all the votes, and the rule is simple: absolute, total, 100% unanimity. If every single participant votes yes, then the coordinator decides to commit. The transaction is a go. But if even one participant votes no, or just doesn't answer in time, the whole thing is off. The coordinator decides to abort.
And that brings us to phase 2. The coordinator broadcasts its final, irreversible decision to everybody. If the decision was commit, every participant makes their temporary changes permanent. If the decision was abort, they just throw those temporary changes away. Either way, everyone ends up in the exact same state. Atomicity guaranteed.
Okay, I know this might sound like a bunch of nerdy technical back and forth, but this protocol, and others like it, are the invisible engine that runs our digital lives.
I mean, really think about it. When you book a flight, a bunch of different databases for seating, payment, schedules, they all have to be updated perfectly. That's a job for a protocol like 2PC. The same goes for your online banking, your cloud storage on Dropbox or Google Drive, even the massive systems that do weather forecasting. They all depend on these rules to keep data consistent and reliable across countless machines.
So the next time you save a file to the cloud or buy something online, you can appreciate this elegant, invisible dance happening in the background, keeping your data safe. But it also makes you wonder, right? Our digital world is only getting more complicated, more spread out. What happens when these fundamental rules that hold everything together are pushed to their absolute breaking point?